So thank you. So I'll begin by giving you a brief outline of my talk today. So this talk is in two parts. First, I'm going to talk about ways to merge stellar mass black hole binaries, and I'll discuss some particular formation scenarios for these mergers, beginning with the evolution of isolated massive star binaries, sort of in the field of the galaxy. Then I'll talk about dynamical encounters in dense star systems like globular clusters, and in particular, a new sort of setting for black hole mergers, which is the centers of galaxies. And the second part of my talk moves from the LIGO regime to the LISA regime for extreme mass ratio in spirals. And in particular, I'm interested in forming MREs by the tidal separation of stellar mass black hole binaries by the supermassive black hole in the centers of galaxies. And I'll talk a little bit about the work that is yet to be done and some conclusions. So here's a plot that you've probably all seen many times. I don't have a pointer, though. Is that okay? I can just use my arm. Okay. Oh, high tech. Thank you. All right, great. Okay, so this plot just shows the comparison of sensitivity curves between LISA, the space-based detector, and LIGO, with which you're all familiar. So, of course, LISA operates at much lower frequency than LIGO does. And since when you're talking about black holes, the frequency of interest goes like 1 over the mass of the object of interest, that tells us that LISA is going to be sensitive to much more massive black holes, so supermassive, in the range from about 10 to the 5 to 10 to the 8 solar masses. On the other hand, LIGO is more sensitive to stellar mass black holes, and we'll say that that's a range between about 30 to 50 solar masses. So in this first part, I'm talking about the LIGO regime, merging stellar mass black hole binaries. And the main point that I want to make is that in dense stellar environments, mergers are going to be biased towards the higher end of the stellar mass spectrum. In this case, that means that the frequency is lower, so the last few orbits in the in-spiral, the merger and ring down are going to play a particularly important role. So numerical relativity is very essential in determining these waveforms. So there are several pathways to merging stellar mass black hole binaries that I'll discuss. First, the evolution of isolated massive star binaries that are isolated in the field, then dynamically triggered mergers in dense star systems, and finally, this new channel in galactic nuclei. So we'll begin with the massive stars. So here's a nice artistic illustration of a massive star binary. As you know, the lifetime of the star goes like 1 over the mass to the 2.5. So the more massive a star, the less time it lives. So the question is, since we see evidence, we have lots of observations of massive star binaries, we're not sure how that translates to black hole binaries. It turns out that just taking a massive star binary and letting it evolve does not guarantee that you're going to end up with a double black hole binary that's tight enough to merge on its own. So one group that's doing a lot of work in trying to determine whether that is actually the case is this CaJAGWR group over at Northwestern. And they use population synthesis codes to take a look at massive star binaries, allow them to evolve, and determine what the end result is. So they take into account the details of mass transfer, supernova effects, and also the common envelope phase. And that's where massive star binaries run into difficulties when you're interested in producing stellar mass black hole binaries. So this common envelope phase involves your two massive stars. If one of them evolves off the main sequence, then you have your massive star in a pair with a stellar mass black hole. Well, that can orbit around for a while, and it's just fine. But when the secondary star then evolves, it becomes a giant, and its envelope is so large that the stellar mass black hole actually orbits within the envelope of its companion, which produces a drag and can cause the two to merge, therefore not creating a stellar mass black hole binary. So the details of this common envelope phase are difficult to deal with, but when they're included in the simulations, it turns out that this can greatly inhibit the formation rate of black hole binaries that are close enough to merge on their own. So while Massive star binaries are nice because we have observational constraints. We know that they exist. Therefore, it's possible that they will create black-hole binaries. Since the common envelope phase is an uncertainty, the rates vary a lot from this merger path. In fact, the detection rates from this same group vary from 1 to 500 per year for advanced LIGO. So when they actually do merge black-hole binaries, I have here their chirp mass distribution from the 2007 paper, and you can see that there isn't a lot of variation in their chirp mass range. And actually, so it's flat across here, and there's a cutoff at just past 8.5. So these are actually low mass black holes that are merging in their simulations. The chirp mass for a binary consisting of 2 10 solar mass black holes is there. It's about 8.7. So these are all fairly low mass binaries. So that's something that will be important to remember later. So we've covered the evolution of isolated massive star binaries. So let's move on to dense star systems where binaries will have multiple encounters. These star systems range in size and mass all the way from globular clusters to the centers of galaxies, of galactic bulges. One subset of galactic nuclei are in smaller galaxies, these nuclear star clusters, and all of these are promising hosts for emerging stellar mass black holes. Being dense star systems, they also all share common dynamical processes, and I'll spend a little bit of time talking about that now. In particular, if you're interested in binaries and figuring out what happens to binaries in dense star systems, one of the most important determining characteristics of that binary is going to be whether it's hard or soft. So hard binary is just one for which the internal energy, the binding energy of the binary is larger than the kinetic energy of the surroundings, so the stars that it's going to interact with. And for a soft binary, the opposite is true. So you see, I just wrote here, if you wanted to get an idea of the sizes that we're talking about, if you have a binary with 2 10 solar mass black holes interacting with 1 solar mass third objects at a speed of about 10 kilometers per second, a hard binary will have a semi-major axis of about 100 AU. Another thing that is interesting to note is that you can change, if you look at for instance, the soft binary requirement. You can change whether a binary is hard or soft without changing the internal properties of the binary. Just by having faster encounters, a binary becomes softer. So that is something that will come into play later as well. So whether a binary is hard or soft actually determines the outcome of three-body encounters. Hard binaries, for instance, typically harden as a result of three-body encounters, so they tighten further. We can get an idea of why this is by thinking about equal mass objects. So in the case of a hard binary, the initial binary orbital speed is high compared to the interloper's interaction speed. On average, at the end of an encounter, the interloper is going to leave with roughly the initial binary orbital speed. So since it's gained velocity, it's taking energy away from the system, causing the binary to harden and become more tightly bound. On the other hand, with soft binaries, they typically soften as a result of three-body encounters. And you can think of this sort of in terms of energy equipartition. The fast-moving interloper comes along and dumps energy into the binary, causing it to widen. Since a soft binary is wider after three-body encounters, that increases its cross-section, making it more likely to have a subsequent encounter. So softening is actually a runaway process. Each encounter is going to cause it to widen, which makes it more likely to have yet another encounter. So this widening can be catastrophic, leading to ionizations of binaries. In the event of an exchange, when the masses are roughly comparable, the final binary is typically going to consist of the two most massive objects. So massive objects tend to exchange into binaries. And this has been shown, especially in the case of globular clusters, to be true by lots of groups. Some relevant timescales here. For dense star systems, the relaxation time tells you roughly how long it takes for large-scale dynamics to occur. These large-scale dynamics can just be, for instance, the sinking of a massive object. So I have here the relaxation time. You can see that more massive objects will relax more quickly. Another relevant time scale is the amount of time that it takes for a binary to merge on its own by gravitational radiation. Most of you have certainly seen this, that if you increase or decrease rather the semi-major axis or increase the eccentricity of a binary, you can greatly reduce the in-spiral time by gravitational radiation. So here's a little illustration of how dense stellar environments can lead to mergers of stellar mass binaries. So you have your binary that's going along here and having multiple three-body encounters. Each encounter changes the value of the eccentricity, and so the eccentricity wanders around. If the pericenter distance after an encounter is small enough, then gravitational radiation takes over, and the in-spiral time will be shorter than the amount of time to the next encounter. So globular clusters being dense collections of stars and also old populations, so you have should have lots of evolved, or stars that have evolved off the main sequence rather, are promising hosts for dynamically triggered mergers. Massive objects are going to sink to the center and have repeated dynamical encounters. But there are some uncertainties as to rates of black hole mergers in globulars. And one of the main reasons for that is that we don't know if globulars can hold on to their black hole populations. So we can say that observations of black holes in globulars are rare. That doesn't really mean a whole lot since black holes like to hide, but it does bring some element of concern because globulars are small. The escape speed of a globular is typically going to be less than 50 kilometers per second, so it raises the question of whether supernova kick black holes out of globulars at formation. In fact, there is at least one example of a black hole X-ray binary that received a 100 kilometer per second kick from its supernova. So we're not sure if the black holes are in globulars and just hiding, or if they've been expelled. And also, since these, if black holes are in binaries and having three-body interactions, that imparts recoils, which can also kick them out of globulars. So we've discussed how to merge black holes in dense star systems and the uncertainties there. So what about trying to find a system that has similar properties to a globular cluster but won't have this problem with retaining its binary fraction or its black hole population? So one such promising environment is galactic nuclei, and in particular, small galactic nuclei, or the nuclei of small galaxies. There's been a lot of work on trying to look into the centers of small galaxies to try to pin down whether galaxies all have massive objects in the centers. So you're probably all familiar with the M-sigma relation, which ordinarily compares the mass of the supermassive black hole to the mass, or to the velocity dispersion of galactic bulges. Well, it turns out that in the centers of commonly in the centers of small galaxies rather, there are clusters of stars that also fall on this M-sigma relation. And a recent survey found that roughly 50 to 80% of small galaxies have nuclear star clusters at their centers. The velocity dispersions in these clusters range from about 13 to 30 kilometers per second, and there are about 6 examples that have velocity dispersions greater than 25 kilometers per second. So like globular clusters, nuclear star clusters have short relaxation times. Massive objects are going to sink to the center, so we expect to have concentration of massive objects in the center. But, and also like globular clusters, they might not contain massive black holes. Massive black holes can do a lot to sort of wreak havoc on binaries by increasing the encounter speed and therefore making it more likely that binaries will ionize, for instance. So nuclear star clusters don't have that threat lurking at the center. But unlike globulars, they have larger escape speeds from about 100 to 200 kilometers per second, so they're going to be holding on to their black hole population. So to that end, I've done some work on nuclear star clusters to try to determine whether it's likely to have black hole mergers within them. I do this using three-body simulations. So black holes are going to be exchanging into binaries, and then those binaries have subsequent encounters with stars or white dwarfs, neutron stars, or even other stellar mass black holes. And basically, what I've done is try to determine what the outcome of those of those encounters will be. So I start with a black hole and its companion. The companion doesn't have to be another black hole. And draw all three masses, including the interloper mass, from a distribution, and then allow that binary to have a series of close encounters with third objects until either the binary merges by gravitational radiation, until it's ionized, or until it's ejected from the nuclear star cluster. And these simulations are done with an n-body integrator, that's HN-body, and also with a driver code, a binary single scattering code, IABL, which basically tracks the properties of the binary, the semi-major axis and eccentricity, and also keeps track of the outcomes, so ionizations, mergers, and exchanges. And here are some results. This is one set of runs here. On the left vertical axis, we have the fraction of binaries that are retained by the nuclear star cluster. The horizontal axis is the escape speed, so we actually did a wide range of escape speeds representing different types of clusters. Then on the right vertical axis, the number of single black holes that are ejected for each pair that merges. So this red curve corresponds with the retained binary fraction, and the blue curve corresponds with the number of singles that are ejected. And this is for one particular initial mass function, basically. This green box represents what we perceive to be the range of escape velocities for nuclear star clusters. So you can see that nuclear star clusters retain the vast majority of their black hole binaries. So mergers are going to be taking place within the cluster rather than outside after they get kicked out, which is the case in globular clusters. Also note that down here, with the number of singles that are ejected per merger, once you get up above about 150 kilometers per second for escape speed, only one or two single black holes is ejected for each pair that merges. So that means that more than 50% of the black holes in these systems will actually merge. On the other hand, this green box is right down at 50 kilometers per second, so this represents sort of the upper end as far as the most massive globular clusters around. And we see that, press this again, they retain very few of the stellar mass black hole binaries and eject almost 25 single black holes for every black hole binary that merges. So it's much harder for globulars to hold onto their black holes as predicted.
Can you explain a little bit more about nuclear star clusters?
Sure.
So they're in the nucleus of galaxies in addition to a supermassive black hole?
No, there is no supermassive black hole. There's no evidence of a supermassive black hole. So basically, the mass of the nuclear star cluster is still on that M sigma relation. So yeah, so it falls on the same correlation. But it's just a collection of stars. So it's basically like a big globular cluster at the center of a small galaxy.
So it's big, and that's why it's big.
It's more massive, yes. And also, yeah. Sure. Okay, so in our simulations, we also find that black hole binaries undergo frequent exchanges. So black holes exchange into the binaries, making it the case that the binaries that merge often involve two massive stellar mass black holes. So I have here, well, the average mass of the binaries that merge is about 30 solar masses. That's set by the top end of the black holes that we allow to be, or the most massive that we allow black holes to be in the simulations. So for about 30 solar masses at a redshift of 0.5, the frequency at ISCO is 100 hertz. So that's here on this green bar. So as you push the mass down, or the mass up, and the frequency down here, so if you allow for more massive black holes, you're going to lower and decrease this frequency. You're pushing up into the region of less sensitivity. So that's why the in-spiral, the last few orbits, the merger and ring down, are going to play an important role. So really hoping for numerical relativity to tell us what the waveform is going to look like there. And we expect several tens of events per year from this with advanced LIGO. So just to give an idea of the differences between this model and the model of isolated binaries, I am showing you again the distribution of chirp masses. Yes, Dr. Marks.
Excuse about something. Sounds like your simulation starts with black hole binary. So the fundamental issue is
Actually, we start with we start with single black holes and let them exchange into binaries dynamically. So the single black holes sync and interact with main sequence binaries, and then replace the main sequence stars, and then go on in the new binary to have further interactions.
So the main sequence star, which then evolves and goes off main sequence, could have the other one effect.
Could, yes.
You don't have the same scale of effect on 500.
Well, it doesn't have to be a massive star in the binary. So the main sequence stars, actually, since there are already black holes around, we know that the really big massive guys have already evolved. So the stars that we're talking about are going to be average mass. So we're not really worrying that much about evolution in that process because the exchanges happen fairly quickly. Okay.
Can I just ask one
Yes.
more about nuclear star clusters?
Yes.
So these are in small galaxies that don't have a supermassive black hole.
Right.
And what do you think the ratio of ones that do to ones that have nuclear star clusters?
Well, let's see.
Because nowadays people say that there's a supermassive black hole in the center of pretty much every galaxy, or at least a big one.
Right. That's the caveat, that they have to be big. So galaxies with bulges have supermassive black holes. That's the relation that Tremaine, for instance, has been working on, showing that there's an occupation fraction of 1, basically, for galaxies with bulges. But the work that's been done for nuclear star clusters is down at the much lower mass end. So there aren't any bulges there, and people, when looking for supermassive or for evidence of supermassive black holes and haven't found it, but have found evidence for nuclear star clusters. All right, so just a reminder that the chirp masses found from the isolated evolution of massive star binaries are less than 9, whereas in dynamical interactions in dense star clusters, we find a chirp mass that's up close to 14. And as I mentioned, it's possible that there are higher mass stellar mass black holes than 20. 20 is just an upper limit that people have chosen, but that it isn't a hard limit. So if there are higher mass black holes, those are going to be the ones that exchange into the binaries. So whatever the most massive black holes that are around, those are going to dominate the mergers. So we've been talking about inducing mergers in small galactic nuclei. We can consider that done. What about larger galactic nuclei that contain supermassive black holes?
Can you have one black hole undergoing multiple mergers?
Well, that is a question that remains to be answered because there are uncertainties with regards to the kicks that people here have done a lot of work on, I'm sure. So I don't think so. Since the escape velocities are only 1 to 200 kilometers per second, the kicks that are found, of course, depending on the orientation, can be much higher than that. So it's unlikely that you're going to be building up, having multiple mergers in these smaller nuclei. So in a more traditional galactic nucleus, you have about 10 to the 6 to 10 to the 7 stars. And like globulars, these are very dense environments, number densities of 10 to the 4 to 10 to the 6 per cubic parsec at a distance from 1 parsec from the center. And also, like globulars and nuclear star clusters, you're going to have massive objects sinking into the centermost regions. But the difference here is that you have a massive black hole waiting there, somewhere between 10 to the 5 to 10 to the 8 solar masses. And the influence that massive black hole has is changing the encounter speeds. So the velocity dispersion goes like 1 over the root of the distance from the supermassive black hole at the center. And also, massive black holes can tidally disrupt the binaries. So those are 2 ways that supermassive black holes can mess up binaries. within a few parsecs of the center of the galactic nucleus, you have as many stars as contained in the entire Milky Way globular cluster system. So there's a lot of ammunition, if you will, for having lots of dynamical interactions. The sinking takes place over the course of relaxation time, and the relaxation time for a stellar mass black hole is going to be about 1/20th that of your average star. So black holes sink very quickly to the center, much less than a billion years. Galactic nuclei also have large escape velocities. They can be many hundreds of kilometers per second. And if 1% of the black holes in nuclei merge in 10 to the 10 years, then advanced LIGO should detect 1 per year. Now, this 1% is just a low estimate to show that this is a viable mechanism. So I've done some more simulations here. These simulations are in nuclei with supermassive black holes. I have been using equal mass binaries that'll change shortly. And I have here the results of several sets of simulations, 2.5, 2.10, and 2.20 solar mass black holes. And I start with a logarithmic range in initial semi-major axis. And the reason why I did that is that when you observe massive star binaries, you find that there are equal numbers in bins of log A. So we don't know if that maps directly to black hole binaries, but it's a good place to start. So we find here, I've just put the merger results. There are other possible outcomes in this scenario that fill in the rest of this table that I've sort of grayed out here. But when looking at the mergers, it's not surprising that if you are more massive or start off much smaller, it's more likely that you're going to merge. In fact, I put the in-spiral time for an isolated binary with each of these initial parameters in this rightmost column. And in white, anything that's in white is something that would merge in isolation within a Hubble time anyway. But take note that the numbers that are in yellow are much greater than a Hubble time. So in particular, let's look here. For the case of 2.10 solar mass binaries at an initial separation of 0.1 AU, 44% will merge by dynamical encounters, whereas if they were left by themselves, it would take 10 to the 10 years. So we see that dynamical encounters are actually an important catalyst for emerging stellar mass black hole binaries.
This is the case where the hardened orbits get more hard.
Yes, they get hardened. Not only are they tighter, but each encounter has the possibility of jostling the eccentricity around, so the pericenter pass can be quite small. So this is just to reiterate here, looking more closely at the 10 to 10 case, that tight binaries merge after just a few encounters. Well, saying one encounter here isn't really that realistic, since that binary would have merged by itself anyway. But in the other cases, it can take just a few hundred or a few encounters to cause these binaries to merge. So to recap the first part here, we've been talking about ways to merge stellar mass black hole binaries. Once again, the formation of close, isolated double black hole binaries in the field is uncertain due to these common envelope problems, but dynamical encounters in dense star systems are quite promising. There are some caveats with globulars, but galactic nuclei in particular are quite promising. Again, multiple encounters in these dense star systems will lead to exchanges, so we expect that the mergers will be biased towards the high mass end. And once again, that brings up the importance of numerical relativity in determining the waveforms. Some key questions remain, especially with regards to galactic nuclei that contain supermassive black holes. So one thing that I'm working on is no longer having just a single mass distribution as far as the interlopers. So I'm going to be adding a mass distribution and taking mass segregation into effect, and also allowing for dynamical formation of black hole binaries. So that's something that I will continue to work on. So in galactic nuclei that have supermassive black holes, there are many possible outcomes. We've already talked about the interactions leading to hardening and possible mergers. Also, the fact that there's this big gravitating object at the center, increasing the encounter speeds can lead to ionizations. But also, there's a possibility that the binaries will reach the supermassive black hole at the center and thereby become a Lisa source. So that's what I'm going to talk about in part 2 of my talk, extreme mass ratio end spirals, or EMRIs. The main point here is that binaries will deposit black holes far enough away from the supermassive black hole that they have time to spiral in and circularize, meaning that LISA events formed by the tidal separation of binaries are going to be circular in the sensitivity band. So MRIs are a primary target for LISA. They just occur when you have a low mass object that spirals into a massive black hole. Stellar mass black holes being the most important such small object, since the strength of the signal is going to go like the mass of the object that spirals in. So the more massive, the more distant we can observe these objects. And of course, MRIs are excellent probes of general relativity in the strong field limit, since the lighter object acts as a test particle and traces out the space-time around the rotating supermassive black hole. So there are three formation mechanisms that I'm going to talk about today. The first is the sort of traditional MRI formation scenario, two-body capture. That's where you start with a single stellar mass black hole that's orbiting around in the nucleus. If it has a very close pass by the supermassive black hole, it emits gravitational radiation and forms this very long extended orbit that, if left alone, would spiral in and merge. So the pericenter distances are typically quite small, about 1/10 of an AU, and the apocenter distance can be quite large, 1/10 of a parsec. So since this stellar mass black hole, after it's on this orbit, is going to spend most of its time out here at apocenter, that leaves it very susceptible to perturbation by passing stars, which can either cause the orbit to be knocked out of this eccentric configuration into an orbit that won't spiral in any reasonable time, or this black hole can be caused to plunge directly into the supermassive black hole. And in either case, no detectable MRI is emitted. But if the binary, or if this potential MRI does in fact spiral in and reach the LISA sensitivity band, they're eccentric in that band and have arbitrary inclination.
How is that eccentricity achieved? Is that the first part of the talk, or how do we achieve this situation?
Oh, here? The reason why it's so eccentric is that it has to get rid of its excess orbital energy by having a really close pass here and emitting gravitational radiation at this point when it just comes in and wanders in close to the supermassive black hole. So its initial pericenter distance is tiny, and it comes out and has this really elongated orbit. So another formation scenario involves accretion disks around the supermassive black hole. If you have a stellar mass black hole that is plunging through the disk, it'll damp out its orbit, and eventually spiral in this plane and settle in the disk. And that also creates, that will create rather, a circular MRI that's in the plane, so also zero inclination. And finally, this binary separation picture, which we originally talked about in 2005, in which you begin with a black hole binary, and it comes in and only has a close enough pass so that the supermassive black hole can tidally separate the binary. You don't actually have to dissipate any energy. You just have to separate the binary so that one of the objects is flung off at a high speed, soaking up that excess orbital energy, and then the other is caught onto this much more modest potential MRI orbit. So the pericenter distances in this instance are going to be about 10 AU, and the apocenter can be about 1,000 AU. So since it starts off, this pericenter distance is well outside the LISA sensitivity band. It spends a lot of time circularizing as it spirals in. So when it reaches the sensitivity band, it's circular, but we still have this arbitrary inclination. So it's interesting that these three different MRI formation scenarios actually produce three very distinct types of MRI signal. So again, just to reiterate, the two-body capture case creates eccentric and inclined MRIs. The accretion disk is circular and in the plane. Binaries create circular but inclined MRIs. So the question that I have, not being a data analyst, but being in a room full of data analysts, I can ask whether it's possible to search specifically for these non-standard scenarios, and if that might simplify data analysis and searching for MRIs. So in particular, if we're not worried about this case with eccentric and inclined events that will have complex waveforms and require some huge multitude of templates, would it be useful to search specifically for these non-standard formation scenarios? And if those non-standard scenarios produce many events, then would this simplification where you're allowed to search over fewer parameters really improve your signal to noise and help with the data analysis aspect? So that's a question that I'd love to have conversations with any of you about afterwards. So before the binary reaches the supermassive black hole at the center of the nucleus, it's going to have many three-body encounters. So I've done simulations that track what happens to the binary as it sinks. Here's a plot of the semi-major axis, the center of mass of the binary around the massive black hole, versus the pericenter distance. So this just shows the binary in this blue curve sinking towards 0, 0, where the supermassive black hole is lurking. One thing to remember is that the presence of the supermassive black hole speeds up the encounters in these interior regions. So as you get closer and closer here, the encounter speeds increase, which means that the binary becomes softer and softer just through the process of sinking. So what happens internally to the binary itself? I added to the plot the binary semi-major axis, which is this red curve, and we can see that each encounter sort of jostles the semi-major axis around. In this region, with a little bit of ups and downs, there is a fairly consistent decrease in semi-major axis. So it's tightening in that region. That lets us know that the binary is hard in that region, since hard binaries harden. But then once we get down to these very centermost regions with high encounter speeds, those encounters are going to typically soften the binary, and we see that each encounter causes the binary to widen and widen further. So it really is sort of a race between the sinking of the binary towards this, the point of tidal separation, and the increase in speeds, which would widen and threaten to ionize the binary. So in this case, the binary sinks to the supermassive black hole and is tidally separated before it's ionized. So we can go back to running multiple sets of these simulations to get an idea of what happens to binaries in nuclei with supermassive black holes. So once again, these are equal mass binaries for now. We see that exchanges and ionizations really are not that important here. That's really not that surprising, I suppose, because we're doing only single mass population for interlopers, and they're one solar mass. It's just not really massive enough to disrupt these black hole binaries. So we see very few exchanges. In this case, for the lowest mass binaries that have the largest semi-major axis to begin with, we see about 22% are ionized in these innermost regions. But even so, the vast majority are not exchanged or ionized. What's known about the mass of stars? So we see evidence in our own galaxy of very massive stars near the supermassive black hole, more massive than you might expect. We expect that the mass distribution is going to favor more massive objects in the centermost region. So that's why all of these simulations where the binaries are interacting with one solar mass objects is really just a first cut, because you have to include the effects of mass segregation. As the binary sinks, in reality, it's going to be interacting not only more quickly or with faster encounter speeds, but with more and more massive objects, which will probably increase the softening a great deal. So that's something that remains to be done, that I'm working on. So in fact, it's not exchanges or ionizations that play a big role, but sort of a trade-off between tidal separations and mergers. So we see here that whether a binary is tidally separated or merges by gravitational radiation is really determined by its initial mass and how large the binary is to begin with. Once again, it's not really unexpected. but it's nice to see the trend. So in the case, once again, we have here, I showed you the first cut with just the mergers. So when you have very massive objects that start off close to one another, they're nearly all going to merge. But as you make the initial semi-major axis larger and larger, it's less likely that they're going to merge by gravitational radiation, and the tidal separation becomes a more dominant outcome.
And that when they're tidally separated, does one of them almost always get captured by the
Yes. In fact, we see here, so the size of the binary determines how far away it is when the supermassive black hole tidally separates it. So that's what this column is here. The pericenter distance is the point at which it's separated. So we see here for very large initial binaries, they're separated at a greater distance from the supermassive black hole. And I calculated the merger time here. So even though this looks kind of big, in this instance where you're starting with 2 10 solar mass objects, a tenth of an AU apart, this potential emery would actually in-spiral in about 6 billion years. So there is a lot of future work that's left to be done here. In particular, I need to do some simulations in galactic nuclei that contain supermassive black holes and take into account the effects of mass segregation and also drawing from a mass population. So these higher mass objects, once they're concentrated in the center, as you mentioned, they're going to have encounters with more and more massive objects. And so I'll be working on the results of how that affects mergers and tidal separations. So in conclusion, this one physical scenario of starting with having black hole binaries in an environment of a galactic nucleus produces 2 different types of gravitational radiation sources. In the case of merging stellar mass black holes by repeated dynamical encounters, we're producing LIGO sources near the high mass end of the binaries. And then if the binary instead reaches a supermassive black hole, we produce emeries and LISA sources. So that's kind of a cool thing to get 2 different types of signals from the same physical scenario. And finally, it's important to keep studying these mechanisms because we need to get an idea of different data analysis techniques and really maximize the potential with the upcoming LIGO detections. Thank you very much.